All right, here we go with lesson notes for section 4.1 and 4.2. A quick side note before we get started. Since IB lingo tends to be a little different on some areas, good thing to know, the main one is this. So they don't refer to radicals as radicals. They call them surds. So if ever you see in directions to write your answer in surd form, that is the same thing as saying simplest radical form. So real quick, let's just skim through the rules of exponents that you've seen quite a bit now in the past. So you know that anytime you multiply two bases that are the same, you can add their exponents. Anytime you are dividing common bases, you can subtract their exponents. And then a power raised to a power, you multiply the exponents. Part D just takes a couple of those and just kind of combines them together. Just remember that anytime you have parentheses, the exponent would belong to everything in parentheses. So if I have 3 to the second power, I also have x to the fourth to the second power. So I've got to apply the 2 to both of those in order to see this answer. Same idea on this. Multiplying the 3 times the 5 to get the top value, and then 4 times 5 to get the bottom value. When it comes to fraction exponents, remember that a fraction exponent is the same thing as a square root. So whatever that number is on bottom is the same as having a root. So if we said 16 to the 1/4 power, that is the same thing as the 4th root of 16. So when you have those fraction exponents, the item on top is the power, and the guy on bottom is the root. The way that's always stuck in my head is simply to remember, if you think of a root like a tree root, those are always underground, so that's what's on bottom. And then exponents we always see above a number, and so I always remember the top number is an exponent. So if I were to do that with this one here, that means 2 is the power and 3 is the root. And it doesn't matter which order you apply this in, you would still get the same answer. The easiest way, though, is to do the root first. So I would say the cubed root of 8 is 2, and then 2 squared is 4. But you could do it either direction and you'd still get the same answer. 8 squared is 64, and the cube root of 64 is still 4. Negative exponents, all negative exponents do are create a reciprocal. So 1/3 of the negative 1 power would just cause it to be 3 over 1. So one more example of that, 2 to the negative 4th. So we get the reciprocal right here, so now it's 1 over 2 to the 4th. And then always simplify whenever possible. So just a few practice examples right here. So this is the part where I would encourage you to stop the video and give the next few a try on your own. So for the first one, 2 things going on. One is the negative exponent. You also have the fraction exponent. So that, remember, the negative is going to put the whole thing on bottom. 1/2 power is the same thing as a square root. So square root of 49 is 7. Same thing with this guy. If this fraction could be reduced, then you're allowed to do that, but in this case it can't. So I would just apply the exponent to each term individually, as you see right here in this setup. Remember, the root is the guy on bottom, exponent is on top. So on top I would say the cubed root of 8 is 2, and 2 squared is 4, so that's going to be my numerator. And on bottom, the cube root of 27 is 3, and 3 to the second power is 9. So we get that look right here. So same thing on part C. So you got the negative, which is going to flip the fraction. We know the square root of 25 is 5, and 5 to the 3rd power is 125. You can see down at the bottom, that number is going on bottom because of the negative exponent. And then same thing with the 9. Square root of 9 is 3. 3 to the 3rd power is 27. That guy's moving up top. All right. Properties with radicals. So just basic multiplying radicals. So as long as they are both radicals, you can always multiply. So you get square root of 15 on something like that. Again, you can always divide as long as both of them are the same root. So this is a square root and a square root, so I can divide and get the square root of 7. when it comes to adding, very particular, they must be the same root and have the same base under the root. But in this case, it's the same idea as adding like 3x plus 9x. The x doesn't change. You only add the coefficients, or the numbers in front. So 3 root 11 plus 9 root 11 is just 12 root 11. The root wouldn't change. And then again, just a few more examples down here. Again, this would be another good time to pause the video if you want to give a couple a try on your own before I go through them. But again, you got two rules going on here. We have the negative exponent, so we're going to cause everything to flip. And then I also got the fraction exponent, and so we've already seen what to do with those as well. So there's a couple different orders you could do this in. This is the way I would do it. So I would start with the negative and I would just flip everything. And then now I would apply the 3/4 power to all my terms. So if we did 4 times 3/4, we would get a power of 3. So that's what you're seeing right here. I have the 8 times 3/4. It's going to give you the 6 that you see right there. 81 to the 3/4 power. Remember, that would mean the 4th root of 81, which is 3. And then 3 to the 3rd power would give you the 27. When you have, same as the one before, but anytime you have a mixture of regular numbers and variables, you just separate the two and just do each one on its own, and then you can kind of bring it back together for your ending answer. So in this case, we could start out by dealing with the cube root of 128. So we're going to separate that term out first. So cube root of 128, if we were to take 128 and break it down into a perfect cube number, which is 64, and a non-perfect cube number like 2, then it gives us something we can work with. So we know the cube root of 64 is 4. So that part gets to come out. You cannot simplify the cube root of 2, so we have to keep that as just the cube root of 2. If I go to the x next, I have the negative 6 power. So remember, a cube root is the same thing as a 1/3 power. So we can rewrite that into this form, and that might be easier to work with. So if I multiply those together, it's going to give you this look right here. Because it's negative, right? Negative means reciprocal, so I'm taking the x, putting it on bottom so that my power becomes positive. Over here we got some adding and subtracting. Remember what we set up above. You're only allowed to add or subtract radicals if they have the same root and the same value under the root. So in this case, in order to do this, these would all have to be the square root of 2 in order to do this. So the first one we're just going to leave alone for a minute. That middle term, if you can see 50 as the same thing as 25 times 2, well, we know the square root of 25 is 5, and then the square root of 2 we would just leave behind. Same thing for the third term. 98, same thing as 49 times 2. We know the square root of 49 is 7, so we bring out the 7, and we're just going to multiply it times the 4 that was already out there. And then you got the 2 root left behind. Since all three of those have square roots of 2, we can just combine all three together to get the last part that you see here. If only 2 of those were the same, and say the third one was not, you would just combine the 2 that are the same, and then just keep the extra ones separated by whatever sign was here, plus or minus. So getting down to the last part of this, just solving some basic equations. I just think basic algebra, you always do the opposite to isolate x. So just because this is times 5, you would divide by 5 to get the next line that you see here. Well, a third power, the opposite of a third power is a third root. So if we took the cube root of both sides, it would look like this. Cube root of 8 is 2. Same thing over here, and again, feel free to pause at any time and try a couple before they're all explained. But again, just basic algebra here. Subtract 7 from both sides. Divide both sides by 3. In this case, we're going to take the 4th root on both sides. Remember, taking a 4th root is the same thing as a 1/4 power. So you could do this either way. You could either say, I'm going to take the 4th root of both sides, or you could say, I'm going to raise both sides to the 1/4 power. Either way, you're going to come out with the same answer. Remember that anytime you have an even root, you got to say plus or minus. Simply because either one of these numbers, positive 3 or negative 3, would fit if I plugged it back into the original equation. Right? That even exponent right there is going to take the sign and make it positive no matter what. So I'm going to get the same value whether I plug in a positive or a negative. So you got to make sure that you throw in the plus or minus anytime you're taking the even root on both sides of the equation. Same thing over here, dividing by 4 first. If I multiply both sides times the third power, or raise both sides to the third power, we can get rid of that exponent right there to solve for x. Of course, with any equation, you can always take an answer and plug it back in to check it. Obviously, I would do that on a test if I had any extra time left over. Last few over here. So again, part D, dividing both sides by 3. Raising both sides to the negative 1/5 power would get x by itself. So fifth root of 32 is 2. And because you had that negative exponent, that 2 is going to go on bottom. Again, over here, add the 28 over, divide by 2, and then just raise both sides to the reciprocal power to get x by itself. And then same idea over here. So you added the 16, did all that. Again, keep in mind on this one, if you have an even root, you got to make sure that you do the plus or minus. So when you took this power here, if I raise both sides to the reciprocal power, that puts the 4 on bottom. Now I have an even root, so now I got to make sure I throw in that plus or minus. And then last two here, as you can see, something like this. You know, anytime you have a variable exponent, typically that's when we will use logarithms to solve, and you could certainly use logarithms to solve a case like this, which you'll be doing down the road here. So, but this is just another approach, and I'll show you why this approach is good to know. On this one, I could solve this with logs pretty easily to solve for x, but another approach is to simply create common bases. Since this has a base of 3, if I can see 81 is the same thing as 3 to the 4th power, right? That's still 81, but now if I write it this way, these guys have common bases. This is an equation, this is equal, so whatever is on the left is equal to whatever is on the right. So that would mean that if their bases are equal, then for this equation to be true, the exponents would have to be equal, which means the x minus 1 would have to be equal to 4, and that gives me the setup that you see right here, and I can solve for x. And you can test it, take that 5, plug it back in, and you'll see that it fits. So here's why that approach is really good to know. A lot more difficult to use logs when you have more than one x within the setup. So this is a great case for using common bases. Since this has a base of 2, I can rewrite 8 with a base of 2. So instead of 8, I'm going to see that as 2 to the 3rd power. Now that I have common bases, well, if the bases are equal, that must mean that the exponents are equal. So 3x plus 3 must be equal to 3 times 5x. And so that's what gives us the equation right here. Ignore the 2's. We don't need the 2's anymore at that point. So we're going to get this look right here. Now we can solve for x pretty easily and come out with our solution for x.